fractal?
A fractal is a mathematical set that typically displays self-similar patterns. Fractals may be exactly the same at every scale, or, as illustrated in Figure 1, they may be nearly the same at different scales. The concept of fractal extends beyond self-similarity and includes the idea of a detailed pattern repeating itself 166. 18. Fractals are distinguished from regular geometric figures by their fractal dimensional scaling. Doubling the edge lengths of a square scales its area by 4, which is 2 to the power of 2, because a square is two-dimensional. Likewise, if the radius of a sphere is doubled, its volume scales by 8, which is 2 to the power of 3, because a sphere is three-dimensional. If a fractal's one-dimensional lengths are all doubled, the spatial content of the fractal scales by a number which is not an integer. A fractal has a fractal dimension that usually exceeds its topological dimension and may fall between the integers. As mathematical equations, fractals are usually nowhere differentiable. An infinite fractal curve can be conceived of as winding through space differently from an ordinary line, still being a one-dimensional line yet having a fractal dimension indicating it also resembles a surface 1548. The mathematical roots of the idea of fractals have been traced throughout the years as a formal path of published works, starting in the 17th century with notions of recursion, then moving through increasingly rigorous mathematical treatment of the concept to the study of continuous but not differentiable functions in the 19th century, and onto the coining of the word fractal in the 20th century with a subsequent burgeoning of interest in fractals and computer-based modeling in the 21st century. The term fractal was first used by mathematician Benoit Mandelbrot in 1975. Mandelbrot based it on the Latin fractus meaning broken, or fractured, and used it to extend the concept of theoretical fractional dimensions to geometric patterns in Nature 405. There is some disagreement amongst authorities about how the concept of a fractal should be formally defined. Mandelbrot himself summarized it as beautiful, damn hard, increasingly useful. That's fractals. The general consensus is that theoretical fractals are infinitely self-similar, iterated, and detailed mathematical constructs having fractal dimensions, of which many examples have been formulated and studied in great depth. Fractals are not limited to geometric patterns, but can also describe processes in time. Fractal patterns with various degrees of self-similarity have been rendered or studied in images, structures and sounds and found in nature, technology, art, and law.
Introduction.
The word fractal often has different connotations for laypeople than for mathematicians, where the layperson is more likely to be familiar with fractal art than a mathematical conception. The mathematical concept is difficult to define formally even for mathematicians, but key features can be understood with little mathematical background. A feature of self-similarity, for instance, is easily understood by analogy to zooming in with a lens or other device that zooms in on digital images to uncover finer, previously invisible, new structure. If this is done on fractals, however, no new detail appears. Nothing changes and the same pattern repeats over and over, or for some fractals, nearly the same pattern reappears over and over. Self-similarity itself is not necessarily counterintuitive. For example, people have pondered self-similarity informally such as in the infinite regress in parallel mirrors or the homunculus, the little man inside the head of the little man inside the head. The difference for fractals is that the pattern reproduced must be detailed 166. 18. This idea of being detailed relates to another feature that can be understood without mathematical background, having a fractional or fractal dimension greater than its topological dimension, for instance, refers to how a fractal scales compared to how geometric shapes are usually perceived. A regular line, for instance, is conventionally understood to be one-dimensional. If such a curve is divided into pieces each 1/3 the length of the original, there are always 3 equal pieces. In contrast, consider the curve in Figure 2. It is also one-dimensional for the same reason as the ordinary line, but it has, in addition, a fractal dimension greater than 1 because of how its detail can be measured. The fractal curve divided into parts 1/3 the length of the original line becomes 4 pieces rearranged to repeat the original detail, and this unusual relationship is the basis of its fractal dimension. This also leads to understanding a third feature, that fractals as mathematical equations are nowhere differentiable. In a concrete sense, this means fractals cannot be measured in traditional ways. To elaborate, in trying to find the length of a wavy non-fractal curve, one could find straight segments of some measuring tool small enough to lay end-to-end over the waves, where the pieces could get small enough to be considered to conform to the curve in the normal manner of measuring with a tape measure. But in measuring a wavy fractal curve such as the one in Figure 2, one would never find a small enough straight segment to conform to the curve, because the wavy pattern would always reappear, albeit at a smaller size, essentially pulling a little more of the tape measure into the total length measured each time one attempted to fit it tighter and tighter to the curve. This is perhaps counterintuitive, but it is how fractals behave.
History.
The history of fractals traces a path from chiefly theoretical studies to modern applications in computer graphics, with several notable people contributing canonical fractal forms along the way. According to Pigkova, the mathematics behind fractals began to take shape in the 17th century when the mathematician and philosopher Gottfried Leibniz pondered recursive self-similarity, although he made the mistake of thinking that only the straight line was self-similar in this sense. In his writings, Leibniz used the term fractional exponents, but lamented that geometry did not yet know of them. 405 Indeed, according to various historical accounts, after that point few mathematicians tackled the issues, and the work of those who did remained obscure largely because of resistance to such unfamiliar emerging concepts, which were sometimes referred to as mathematical monsters. Thus, it was not until 2 centuries had passed that in 1872 Carl Weierstrass presented the first definition of a function with a graph that would today be considered fractal, having the non-intuitive property of being everywhere continuous but nowhere differentiable. 7 Not long after that, in 1883, Georg Cantor, who attended lectures by Weierstrass, published examples of subsets of the real line known as Cantor sets, which had unusual properties and are now recognized as fractals. 11-24 Also in the last part of that century, Felix Klein and Henri Poincaré introduced a category of fractal that has come to be called self-inverse fractals. 166. One of the next milestones came in 1904, when Helge von Koch, extending ideas of Poincaré and dissatisfied with Weierstrass's abstract and analytic definition, gave a more geometric definition including hand-drawn images of a similar function, which is now called the Koch curve, see Figure 2, 25. Another milestone came a decade later in 1915, when Wacław Sierpiński constructed his famous triangle. Then, 1 year later, his carpet. By 1918, 2 French mathematicians, Pierre Fatou and Gaston Julia, though working independently, arrived essentially simultaneously at results describing what are now seen as fractal behavior associated with mapping complex numbers and iterative functions and leading to further ideas about attractors and repellers, that is, points that attract or repel other points, which had become very important in the study of fractals, see Figure 3 and Figure 4. Very shortly after that work was submitted, by March 1918, Felix Hausdorff expanded the definition of dimension, significantly for the evolution of the definition of fractals, to allow for sets to have non-integer dimensions. The idea of self-similar curves was taken further by Paul Levy, who, in his 1938 paper Planar Space Curves and Surfaces Consisting of Parts Similar to the Whole, described a new fractal curve, the Levy C-curve. Different researchers have postulated that without the aid of modern computer graphics, early investigators were limited to what they could depict in manual drawings, so lacked the means to visualize the beauty and appreciate some of the implications of many of the patterns they had discovered. The Julia set, for instance, could only be visualized through a few iterations as very simple drawings hardly resembling the image in Figure 3, 179 that changed, however, in the 1960s. When Benoit Mandelbrot started writing about self-similarity in papers such as How Long is the Coast of Britain? Statistical Self-Similarity and Fractional Dimension, which built on earlier work by Louis Ferry Richardson. In 1975, Mandelbrot solidified hundreds of years of thought and mathematical development in coining the word fractal, and illustrated his mathematical definition with striking computer-constructed visualizations. These images, such as of his canonical Mandelbrot set pictured in Figure 1, captured the popular imagination. Many of them were based on recursion, leading to the popular meaning of the term fractal. Currently, fractal studies are essentially exclusively computer-based.
Characteristics.
One often cited description that Mandelbrot published to describe geometric fractals is a rough or fragmented geometric shape that can be split into parts, each of which is, at least approximately, a reduced-sized copy of the whole. This is generally helpful but limited. Authorities disagree on the exact definition of fractal, but most usually elaborate on the basic ideas of self-similarity and an unusual relationship with the space a fractal is embedded in. One point agreed on is that fractal patterns are characterized by fractal dimensions, but whereas these numbers quantify complexity, that is, changing detail with changing scale, they neither uniquely describe nor specify details of how to construct particular fractal patterns. In 1975, when Mandelbrot coined the word fractal, he did so to denote an object whose Hausdorff-Biesikowicz dimension is greater than its topological dimension. It has been noted that this dimensional requirement is not met by fractal space-filling curves such as the Hilbert curve. According to Falconer, rather than being strictly defined, fractals should, in addition to being nowhere differentiable and able to have a fractal dimension, be generally characterized by a gestalt of the following features. Self-similarity, which may be manifested as exact self-similarity, identical at all scales. For example, Koch snowflake, quasi-self-similarity, approximates the same pattern at different scales. May contain small copies of the entire fractal in distorted and degenerate forms. For example, the Mandelbrot set satellites are approximations of the entire set, but not exact copies, as shown in Figure 1. Statistical self-similarity repeats a pattern stochastically so numerical or statistical measures are preserved across scales. For example, randomly generated fractals. The well-known example of the coastline of Britain, for which one would not expect to find a segment scaled and repeated as neatly as the repeated unit that defines, for example, the Koch snowflake, qualitative self-similarity, as in a time series, multifractal scaling, characterized by more than one fractal dimension or scaling rule, fine or detailed structure at arbitrarily small scales. A consequence of this structure is fractals may have emergent properties, related to the next criterion in this list, irregularity locally and globally that is not easily described in traditional Euclidean geometric language. For images of fractal patterns, this has been expressed by phrases such as smoothly piling up surfaces, and swirls upon swirls. Simple and perhaps recursive definitions see common techniques for generating fractals. As a group, these criteria form guidelines for excluding certain cases, such as those that may be self-similar without having other typically fractal features. A straight line, for instance, is self-similar but not fractal because it lacks detail, is easily described in Euclidean language, has the same Hausdorff dimension as topological dimension, and is fully defined without a need for recursion.
Common techniques for generating fractals.
Images of fractals can be created by fractal generating programs. Iterated function systems use fixed geometric replacement rules. May be stochastic or deterministic. For example, Koch snowflake, Cantor set, Hafferman carpet, Sierpinski carpet, Sierpinski gasket, Pinot curve, Harter highway dragon curve, T-square, Menger sponge. Strange attractors use iterations of a map or solutions of a system of initial value differential equations that exhibit chaos. For example, see multifractal image. L systems use string rewriting. May resemble branching patterns, such as in plants, biological cells, for example, neurons and immune system cells, blood vessels, pulmonary structure, etc. For example, see Figure 5, or turtle graphics patterns such as space-filling curves and tilings. Escape time fractals use a formula or recurrence relation at each point in a space, such as the complex plane. Usually quasi-self-similar. Also known as orbit fractals. For example, the Mandelbrot set, Julia set, Burning Ship fractal, Nova fractal and Lyapunov fractal. The 2D vector fields that are generated by one or two iterations of escape time formulae also give rise to a fractal form when points, or pixel data, are passed through this field repeatedly. Random fractals use stochastic rules. For example, Levy flight, percolation clusters, self-avoiding walks, fractal landscapes, trajectories of Brownian motion and the Brownian tree, that is, dendritic fractals generated by modeling diffusion-limited aggregation or reaction-limited aggregation clusters. Finite subdivision rules use a recursive topological algorithm for refining tilings and they are similar to the process of cell division. The iterative processes used in creating the Cantor set and the Sierpinski carpet are examples of finite subdivision rules, as is barycentric subdivision.
Simulated fractals.
Fractal patterns have been modeled extensively, albeit within a range of scales rather than infinitely, owing to the practical limits of physical time and space. Models may simulate theoretical fractals or natural phenomena with fractal features. The outputs of the modeling process may be highly artistic renderings, outputs for investigation, or benchmarks for fractal analysis. Some specific applications of fractals to technology are listed elsewhere. Images and other outputs of modeling are normally referred to as being fractals even if they do not have strictly fractal characteristics, such as when it is possible to zoom into a region of the fractal image that does not exhibit any fractal properties. Also, these may include calculation or display artifacts which are not characteristics of true fractals. Modeled fractals may be sounds, digital images, electrochemical patterns, circadian rhythms, etc. Fractal patterns have been reconstructed in physical three-dimensional space, TEN and virtually, often called in silico modeling. Models of fractals are generally created using fractal generating software that implements techniques such as those outlined above. As one illustration, trees, ferns, cells of the nervous system, blood and lung vasculature, and other branching patterns in nature can be modeled on a computer by using recursive algorithms and L-systems techniques. The recursive nature of some patterns is obvious in certain examples. A branch from a tree or a frond from a fern is a miniature replica of the whole, not identical, but similar in nature. Similarly, random fractals have been used to create many highly irregular real-world objects. A limitation of modeling fractals is that resemblance of a fractal model to a natural phenomenon does not prove that the phenomenon being modeled is formed by a process similar to the modeling algorithm.
Natural phenomena with fractal features.
Approximate fractals found in nature display self-similarity over extended, but finite, scale ranges. The connection between fractals and leaves, for instance, is currently being used to determine how much carbon is contained in trees. Examples of phenomena known or anticipated to have fractal features are listed below.
In creative works.
Fractal patterns have been found in the paintings of American artist Jackson Pollock. While Pollock's paintings appear to be composed of chaotic dripping and spattering, computer analysis has found fractal patterns in his work. Decalcomania, a technique used by artists such as Max Ernst, can produce fractal-like patterns. It involves pressing paint between two surfaces and pulling them apart. Cyberneticist Ron Iglash has suggested that fractal geometry and mathematics are prevalent in African art, games, divination, trade, and architecture. Circular houses appear in circles of circles, rectangular houses in rectangles of rectangles, and so on. Such scaling patterns can also be found in African textiles, sculpture, and even cornrow hairstyles. In a 1996 interview with Michael Silverblatt, David Foster Wallace admitted that the structure of the first draft of Infinite Jest he gave to his editor Michael Pike was inspired by fractals, specifically the Sierpinski triangle, also known as Sierpinski gasket, but that the edited novel is more like a lopsided Sierpinski gasket.
In law,
If a rule or principle of law is conceptualized as defining a two-dimensional area of conduct, conduct within which should be legal and conduct outside of which should be illegal, it has been observed that the border of that area must be a fractal, because of the infinite and recursive potential exceptions and extensions necessary to account appropriately for all variations in fact pattern that may arise.